In this first video, we want to talk about autonomous systems and their stability. So we are looking at a system of two equations in which we have x and y both depending on time, and we have an information, their derivatives, depending on x and y themselves. So we write this as dx dt equal a function of x and y, and dy dt is equal to another function of x and y. So t is not appearing on the right-hand side. This is called autonomous. And we're expecting f and g to be continuous for some values of x and y in a domain that we call D. So for any x and y in the domain D, f and g are continuous. If we pick an initial condition inside the domain, so if we pick x0, y0 inside the domain of continuity of both f and g, and we assign some initial conditions, so we know that the solution at time t0 is at x0, y0, then there exists a unique solution. There exists a unique solution for some time around that. So what we want to be sure of is that the solution doesn't exit the domain of continuity. If the solution exits the domain of continuity, then we're not sure about the existence of it anymore. But as long as we start inside the domain, then there is a neighborhood in which we know the existence. And if we know the existence, we know the uniqueness. Now that we know that a solution exists, we want to talk about stability and instability. So the first step is we know that special things happen when the derivative of something is equal to 0. In particular, if you start somewhere and its derivative is 0, then you're not going to move from that. So any x that satisfies f of x equal to 0 is a critical point of the system x prime equals f of x, where x can be in this case a scalar as we have seen earlier, but also a vector. So you have to satisfy as many equations as the number of elements in the vector. We say that once you find a critical point, you can look at its stability. So we say that x star is stable if for any ball of radius epsilon around x star, there is a ball of radius delta, such that if you start inside the ball of radius delta, you stay in the ball of radius epsilon. If you start nearby, you stay nearby. So you can start inside the ball of radius delta, and you can swing around, but you're never getting out of the ball of radius epsilon. In this case, delta is smaller or equal than epsilon, because, well, at least at time 0, you are at x0, so delta cannot be bigger than epsilon. But it can be equal if everything is going just straight towards x star. It can be smaller if there are some wiggling around. So this is the concept of stability. If you start there, you don't wander away from it. It doesn't state that you go towards it. You can just be, for example, our center options, the idea of just having an ellipse around the center, that would be a stable critical point. If no such delta exists, then x star is unstable. That means it doesn't matter how close you start with x star, at some point you're going to leave epsilon. Notice that not everything in the center ball needs to be leaving, but it means we cannot find a ball in which all the points stay nearby. Some of it will leave. Some we don't know and we don't really care. If some of them are leaving, then x star is unstable. There's also another thing that we want to talk about is asymptotically stable. So x star is asymptotically stable if not only it is stable, but on top of that, there exists another ball of radius delta 0, such that if you start inside that ball, then you actually go towards x star. The limit for time tending to infinity of the solution started at x0 goes to x star. The norm of the difference tends to 0. This means that if you have your x star and the delta 0, you are doing something but getting closer and closer to x star. You might be doing some spiraling towards it. You can actually go first away from x star and then coming back. But you're not wandering too far because it is stable. So let's look at an example. We're looking at the pendulum. Here we are like hanging the pendulum from a fixed point, and we're computing the angle theta between the vertical and the arm of the pendulum. We're hanging a mass m to this pendulum, and we have two forces on this mass. We have the gravity that is dragging it downwards, and we have a damping factor. So something that is slowing down the pendulum. And that depends on the velocity at which the angle is changing. We are expecting theta to be bounded by minus pi and pi, and we want to find an equation that satisfies, that describes fully the pendulum. So we're going to match the angular momentum with the two forces that we have introduced, the damping, that has a negative sign with respect to d theta dt, and the gravity that has to be multiplied by L sin theta, because we want to look at only at something that is tangent to the connection to our fixed point. So all the component of the gravity force that is along the x that connects us to the fixed point, that doesn't impact at all. The only part we're interested in is the tangent part, the one that is actually moving the mass. So we get to this equation based on F equal ma. The equation for the pendulum becomes ml squared, second derivative of theta with respect to time, so this is our angular momentum, equals minus c times L times d theta dt, that is the damping factor, and the gravity factor, minus mg, the force of gravity times the mass, times L sin theta. So we can do some changes in here. For example, we can divide everything by ml squared, such that the second derivative of theta doesn't have a constant anymore, and turn everything such we have a 0 on the other side. We define gamma as c divided by ml and omega squared as g divided l. And with a change of variables, we now define x as being theta and y being the first derivative of theta. So we went from a second order ODE to a first order 2D ODE. We now have x and y, and we're taking the derivative of x with respect to time and the derivative of y with respect to time, and we have some information about them. So the derivative of x with respect to time, it's y. While the derivative of y with respect to time is the one that comes from our angular momentum equation for the angle, and it's minus omega squared sin x minus gamma y. If we want to look at critical points, we want to find something for which dx dt is equal to 0, so y is equal to 0, and dy dt is also equal to 0. What does that mean? Well, dx dt means that theta, it's fixed. The derivative of theta with respect to time is equal to 0. That means that theta is starting, not moving. And the derivative of y over time is also equal to 0. That means that the derivative of theta over dt is equal to 0. The derivative of theta divided by time is equal to 0. So we are blocking the first and the second derivative of theta equal to 0. That is what a critical point is. We're not moving and we're not accelerating. So to solving the equations, we have y equal to 0 coming from dx dt equal to 0, and we have minus omega squared sin x minus gamma y equal to 0, but y is equal to 0, so we need sin x equal to 0. So x is either 0 or plus or minus pi. That means that the two critical points are the mass hanging at the bottom of our pendulum or the mass being exactly on top. Hanging at the bottom is theta equal to 0. Being exactly at the top is theta equals plus or minus pi. Notice that if you start swinging when you're at the bottom, with the damping, you're going to go towards the critical point. So with what we have introduced, we expect that critical point to be stable. But if you're just next to the critical point that is straightly up, if you're just off it, you're just going to go away from it. You're never going to go back. So that is expected to be unstable. The bottom one is stable and asymptotically stable. Not only you're not leaving the neighborhood, but you're getting closer and closer to the situation, to your equilibrium point.